Okay, so I'm Jessica and I'm going to present on the bomb calorimeter experiment. First I'm going to give you all a little overview and background of it. We're going to be using a par oxygen cone calorimeter. Its purpose is to measure the heat release from a combustion reaction, and then it analyzes the products of that reaction. And it is used to find the heats of combustion of different materials or fuels. And it's commonly used in practice today. So the objective of this experiment is to become familiar with that bomb calorimeter, to know how it works, understand the equations behind it, and then to determine the thermal capacitance of the system, and then use that thermal capacitance to determine the heat of combustion of a sample, an unknown fuel sample. So I'm going to go through some technical background and equations that govern this. So first, the heat of combustion by definition is the number of heat units liberated by a unit mass of substance when combined with oxygen in an enclosure of constant volume. So when we burn something in a small space, the heat it releases is the heat of combustion. So for this experiment, we are going to find that heat of combustion through a calculation that uses a change in temperature of surrounding water to find that heat of combustion. So the first law of thermodynamics, we're all very familiar with that. Energy is conserved. So the energy released in that combustion reaction is going to increase the water temperature through conduction. And the equation, as you can see, is a function of change in temperature. And that's how we're going to find the thermal capacitance. So the thermal capacitance is, by definition, a material's ability to store heat energy. So as you can see, manipulating that equation from the previous slide, the thermal capacitance is a function of heat and change in temperature. And then in this experiment, that heat release is going to be the heat of combustion of whatever fuel you're using, whether it's the known sample or the unknown sample. When it's the known fuel, you're going to use its heat of combustion that you know to then determine the thermal capacitance, which is mass times specific heat. And then when it's the unknown fuel, you're going to use the thermal capacitance you just found in the previous round of the experiment to determine the heat of combustion for that unknown fuel. And then something to pay attention to when we're doing the experiment, the ignition wire used to ignite the combustion reaction does add to the heat of combustion. So in those calculations, you need to be sure to include the heat of combustion for the ignition wire as well. So now we're going to go through some bits of the experimental procedure. The preparation, it was very long and detailed, so I didn't want to go through every step. But I'm going to go through some things to look out for when you're doing it, because you're going to follow each step exactly. But some things to pay close attention to when you're assembling and preparing the bomb part of it. The ignition wire cannot be grounded in the crucible because it will not properly ignite the combustion reaction. You want to ensure there's no water in the crucible with the fuel. And then you want to make sure not to overpressurize the system. It should be at 30 atmospheres. Overpressurizing the bomb could lead to safety hazards. So for the water jacket, you want to make sure that the initial temperature of the water is plus or minus 5 degrees Fahrenheit. If it's not, it could affect your calculations. And then when inserting the water bucket into the jacket, you want to make sure that it's touching the grounding button for it to be properly assembled. Setting up the instrumentation, be mindful of your data recording frequency. You're going to be recording data for 2 minutes before you actually ignite the bomb, so you want to make sure you're not choosing a recording frequency that will give you too much data to analyze. And then when you're assembling it, you should seek help from the instructor before you put it all together to make sure you're doing it properly, because it's very complicated the way you have to assemble all of the different things together with the bomb inside of the water jacket, inside of with the ignition system and the stirrer. And then when you are actually performing the experiment, you're going to log data, like I said, for 2 minutes before you actually ignite the bomb. And then when you ignite it, it has a series of, you have to press the button and there's a certain response you're supposed to get based on the lights and such. And if it's not responding as it's supposed to based on the experimental procedure, you have to take it apart and check the whole circuit for continuity, which could lead to other complications. And then once you ignite the bomb and it ignites properly, you're going to collect data for several minutes, but you want to be sure to stop collecting data before the temperature starts to fall again. So it's going to rise, obviously it's going to heat the water, and then it's going to come to some sort of equilibrium, but it'll start to fall again. You want to stop collecting data before it starts to fall again. And then you want to repeat the whole process with the unknown fuel sample, and then use all of the data that you collected to perform your analysis. So some experimental predictions. So for the thermal capacitance, we were estimating the system to be 2 kilograms of water and 3 kilograms of stainless steel. And based on the numbers here, we got that the expected thermal capacitance would be 9,600 joules per degree Kelvin. And then for the rise in temperature of the benzoic acid, we used that 9,600 joules per degree Kelvin as a thermal capacitance, and then manipulated the first law equation to solve for delta T. And then as you can see, we got that we estimate a change in temperature of 2.75 degrees Kelvin. So some potential sources of error, like I went through with the preparation, it's important to make sure the ignition wire is not grounded to the crucible and that all of the fuel is going to get burned, so you don't want to get any water in the crucible. Those could all affect how much heat is released in the combustion reaction, and as well as having air leaks in the bottom. You don't want to have any air leaks because that could also affect how much heat is released. And then the water temperature at the start, if it's not at that plus or minus 5 degrees Fahrenheit, it could give you an incorrect result through your calculations. Any questions?